Good day. I am Dr. Roger Luyan Jr., and on behalf of the SARAI Project 2.3 team, may we present our webinar, Smarter Technologies for Crop Water Management. There are different technologies that we can use in order to promote and practice smarter irrigation. SARAI has developed different technologies and systems that our farmers can use as basis for their irrigation scheduling and management. First, let us take a look at the Philippine water resources. The Philippines is endowed with abundant water resources with a total renewable water resources of 479 billion cubic meter per year as of 2017. Of this, 92.75 billion cubic meter per year are withdrawn for domestic, industrial, and agricultural use. Around 80% of the total water withdrawal is for agricultural use, and 98.6% alone is intended for irrigation. Irrigated agriculture is on average at least twice as productive per unit of land as rain-fed agriculture, thereby allowing for more intensified and diversified crop production. When water is applied efficiently, production and crop yield are positively affected. However, due to population growth, urbanization, and climate change, competition for water resources is expected to increase with a particular impact on agriculture. There are also gaps in the design assumption used and operational realities of irrigation systems, as well as unaccounted water losses. Over and underestimation of irrigation water requirements occur due to inaccurate measurements of available soil moisture, leading to untimely irrigation. All of this cause a decrease in agricultural water use efficiency and can lead to production and yield losses. With the current challenges faced by the agricultural sector, irrigation water management strategies are the most important way to improve agricultural water use while maintaining optimal production and yield. The key is to implement management strategies that improve water use efficiency without decreasing yield. Irrigation scheduling is one way of managing water application. It involves deciding when and how much water to apply to a field. Irrigation scheduling can be done based on the planting status, the climate condition, and soil water availability. Plant-based methods depend on planting status, such as stage of plant growth or the days after planting. Irrigation application is determined through physical observation of crops, monitoring of days after planting, and scheduling based on previous irrigation activity. This method is commonly practiced by traditional farmers and has been developed through experience and time. Climate-based irrigation scheduling can be based on evapotranspiration or rainfall occurrence. When relying on evapotranspiration for irrigation scheduling, the amount that evaporated or transpired can be estimated using an instrument or by computing for it using meteorological data. Rainfall events can also be a basis for irrigation scheduling by considering the number of days after the last rainfall. Postponement of irrigation can also be based on rainfall forecast. Soil-based irrigation scheduling is based on the actual soil moisture content in the soil and the water requirement of the crop. The traditional method of determining whether irrigation is needed is through the look and feel method, where a sample of soil is taken from the field and observed of its ability to be formed into a ball, a rod, or ribbons, as well as its firmness and color. Another method is using soil moisture sensors that can estimate the volumetric moisture content in the soil by measuring some other variable that can be correlated to soil moisture, such as capacitance, soil moisture tension, or by using the standard gravimetric method of soil moisture determination. More focused discussion will be given to climate-based and soil-based irrigation scheduling in relation to smarter irrigation. To better address the irrigation management problem in the Philippines, SARAI is developing and promoting smart crop water technologies for smart and efficient irrigation scheduling to optimize production and minimize adverse environmental impacts. When water application is untimely or insufficient, it may reduce yield, lower crop quality, and leach applied fertilizers. Smart irrigation entails applying to crops the right amount of water at the right time and in the right place. These strategies allow for the conservation of water and energy and potentially decrease the farmer's operating costs. The practice of smart irrigation promotes the use of modern technologies and development for irrigation water management, advisories and irrigation recommendations that are based on soil, crop, and agro-meteorological data for more accurate analysis. Technologies developed can be evapotranspiration or soil moisture based. Some common smart irrigation technologies are the use of Internet of Things in soil moisture measurement, alternate wetting and drying for lowland rice, installation of drip irrigation or automated irrigation, and near real-time monitoring of water levels. These technologies promote water conservation, high crop productivity, high water use efficiency, minimized labor and drudgery, increase in global competitiveness, and allows youth engagement and women participation in agriculture. Smart irrigation technologies utilizes sensors and instruments ranging from simple to sophisticated designs. Technologies developed by SARAI will be discussed later on. The climate-based irrigation scheduling mainly depends on evapotranspiration, or the sum of evaporation from soil and transpiration from plants. It can be measured directly or indirectly. Indirect method uses empirical models and equations in computing evapotranspiration with different agro-meteorological data. On the other hand, direct method measures the water vapor in the atmosphere. In SARAI, we use the Atmometer, which is a simple yet effective tool for measuring evapotranspiration. An atmometer easily provides data for irrigation scheduling as it measures the reference crop evapotranspiration that is comparable to weather stations. A modified atmometer simulates crop canopy using a diffusion or canvas cover that is placed atop the ceramic evaporator cup. The water gauge located on the side of the cylindrical container can be used for manual measurement, and for electronic atmometers, a data logger is utilized for automated hourly readings. When water evaporates from the wet surface of the ceramic cup, the upward pull of water causes a change in the water level on the side tube. The change of water level on the side tube, or the height difference of water between two periods, represents the amount of water that evaporated and transpired. To have a more accurate data, calibration of the atmometer to the local climate conditions must be done. This is done by utilizing empirical equations such as the Fau-Penman-Monteith equation. The calibrated reference evapotranspiration reading can be used to estimate the amount of water to irrigate the crop by computing for the actual evapotranspiration. The team has developed a web-based ET calculator that can be used to generate an irrigation schedule by analyzing daily evapotranspiration measurements specific to a farm. An atmometer must be installed near the farm or agricultural area being monitored. The farm should approximately be within the 5-kilometer radial coverage of the atmometer. However, geographic and topographical locations must be taken into consideration, such as mountain ranges or bodies of water, as it affects the microclimate of the area. Next is the soil moisture-based irrigation. It is based on the availability of water in the soil for the crop uptake. Soil moisture measurement can be done through gravimetric method or by using soil moisture sensors. Gravimetric soil moisture measurement is the standard method of determining the amount of water in the soil. However, the process is labor-intensive and time-consuming. Hence, the development and use of commercially available soil moisture sensors that can estimate the volumetric moisture content in the soil using other easily measurable variables. Soil moisture conditions can be generalized according to its wetness or dryness. If the soil is saturated, excess water is lost through runoff and percolation. On the other hand, if the soil has reached permanent wilting point, the plants cannot absorb water from the soil anymore. Optimal plant growth occurs between the field capacity and the typical soil moisture conditions, or within the maximum allowable depletion. Soil moisture management levels usually is classified as excess, optimal, stressed, and extremely stressed. The maximum allowable depletion is the threshold or the limit at which plants can extract water, so as not to permit or allow occurrence of water stress. To monitor and accurately manage soil moisture content within the optimal area for plant growth, SARAI developed the WAISS, or the Water Advisory for Irrigation Scheduling System. WAISS is a decision support system which provides site and crop-specific irrigation advisory and crop water management recommendations. The whole system consists of a field unit and a computer software. The field unit is installed in the farm for daily moisture content measurement, usually at lowest area in the field. The field unit is comprised of 2 to 3 soil moisture sensors, a transmitting data logger, and a solar panel. Soil sensors are horizontally installed in the soil based on the crop's effective rooting depth. It continuously measures the soil moisture content. The solar panel serves as a power source and recharges the battery in the transmitting data logger. The logger stores the soil moisture measurements from the sensor and transmits the data to the WAISS server. The server, consisting of a GSM module and software, receives the data from the field unit and analyzes it to generate irrigation advisories. The advisories are then sent to end users via SMS, daily and during critical periods. End users may opt to request for the current status of their farm by texting status to the WAISS server. In setting up the server, certain data about the farm will be provided by the users, such as the farm location, the crop and its characteristics, the soil properties, and irrigation system specifications. Once this user-defined data has been provided, WAISS server will compute and analyze soil moisture measurements from the field unit and will give appropriate irrigation advisories to the end users. For SARAI Project 2.3, the team is currently improving the design of WAISS, both the field unit and software, to fix some issues or problems encountered during field testing, and to improve the software to make it more user-friendly and accessible. Additional field testing for different upland crops will also be conducted for a more accurate application to a wide variety of crops. With the improvement on WAISS, the team is already working on the application for patent for the technology to protect it from infringement. This is also in preparation for its commercialization and mass production. WAISS was initially installed and tested for corn production during the wet and dry season at the Central Experiment Station in UP Las Banas. Furrow and drip irrigation were also installed, accompanying the WAISS testing to determine its effectiveness on irrigation management advisories. WAISS was also deployed in the Mariano Marcos State University in Batac, Ilocos Norte to test for tomato production. Moreover, the team has been calibrating the Atmometer to local climate conditions for Los Baños, Laguna. The calibrated evapotranspiration data measured using the Atmometer were used as inputs for the irrigation scheduling and management in the previously mentioned corn production at the Central Experiment Station in UP Los Baños. For inquiries and concerns, you may send us a message on the email address shown on the screen. Thank you and God bless.